So let's have a brief summary of what I've learned about this harmonic oscillator, right? So we know the Hamiltonian, okay, equals to 1/2 p squared over m, right? Plus 1/2 m omega squared x squared. And then we, in units of LC and PC, okay? So this Hamiltonian can be written as x squared plus p squared. So it's a very symmetric form, okay? Right, and this one, this dimension is the position momentum satisfy the commutator, that is I, okay? And then we can define the late operator, okay? So that equals to okay. It's also dimensionless, okay? And this one actually is equivalent to this commutator, right? So equivalent, you have this commutator, okay? So this is the most important thing about the commutators, okay? So it's the basis of all the other commutators, right? So in this way, the Hamiltonian can be written as h bar omega a deck a plus 1. And this one I call them ladder operators, because we have found that by algebra method, okay, we found that so the energy levels actually form ladder equally spaced, and there's a quantum state with energy that's h bar omega over 2 and 3 h bar omega over 2, 5 h bar omega over 2, 7 h bar omega over 2, 9. Okay, it's continuous. But this one is the quantum state, okay? This is the normal states below this one. If we apply and A diagram here, okay? So it goes to this one. Okay. And if we apply the lower operator, okay, A, okay, that actually goes down to this one. And then of course immediately you know that if you have the quantum state, so you're going to have this one to be 0, okay? Right. So that's the basic things that we have learned, okay? We have also learned the matrix form, okay? So to make the expression shorter, okay, let me introduce a new notation, the direct rotation of quantum mechanics, okay? We have seen that usually we have the states like this one, psi mx, right? For example, you can have something like okay, and then x, sorry. Right. So this is a very lengthy okay, composite. Okay, that's something that if we keep writing all these common states, it's going to be a pretty, you know, composite. But sometimes we just use shorthand notation. For example, just write it as m, right? or even more systematically, Dirac introduce this Dirac rotation. You just say, I use a label M, put this in the cat. So this one is the same as %M, okay? So that one is called a cat state, okay? And then you can do the same thing, right? So we know that, for example, you can apply this state on this one. So that one will change this one to, in the later, this will change this one into M-1, right? Okay. So we know the matrix element. We know that the coefficient is the square root of M. Okay. And similarly, you can act on this one on M using this Racine operator. The result is this one, right? So if we translate this one in the original representation, okay, you can say that this is A acting on psi mx equals to square root of M psi m-1x. It's the same, right? Or A deck psi m plus 1. Sorry. Okay, equals to m plus 1 psi m plus 1 x. Okay. Right, so you can have this kind of cat states, and also you can have this operation on this one. So you can also have actually the so-called brass state. So if you put these two together, it's a bracket. Okay, so this one actually is this one. Okay, so that so if we put the two together, so what does this mean? Okay, so this one actually means integration. Okay, so that one is called a inner product. Okay, right. And so you can also consider, for example, you can calculate the x acting on M. So this gives a new state, right? So this is a state. Okay, and then you put the M right here. Okay, so this one can be denoted as just M x M. So what does this mean? This actually means you put a state M right here, right? Plus mx, and then acting the position operator on the state M and do the inner product or the integration. Okay, right? Okay, so in general, so let me summarize this one a little bit. Okay. Okay, so you can say that I can say M is just the same as percent mx. This is called a cat. We can also have bra. That's M is the same as percent m complex conjugate. Okay. You can have an inner product. Okay. You can have operator action. Okay. This one is the same as okay. Right. You can also have the matrix element. Okay. So this is the direct rotation. Okay. So we're going to use this one more and more, so so that you can get more and more familiar with this kind of rotation. Okay. So direct rotation, right? It's very neat. Okay. So this, of course, that's a good thing. Okay. But more importantly, okay, now this state per se is defined independent of real space. Okay, so you can see that it's just per se is just a possibility. It's not necessary a real space wave function. Okay, so this actually leaves a lot of freedom, make it a lot easier to generalize quantum mechanics to much more complex systems. Okay, and let me give you a few examples. Okay, right. Let me give you a few examples. Okay, of course this one percent mx, you have known this one. This is fine, right? But we can also have a state that has a three-dimensional function. Okay, you can say MLM that equals to percent MLM x y z. So it could be three-dimensional. That has a three index. It could be say vacuum. Okay, that means the possibility of no particle. How do you write with this in a wave function? Right. So this is not possible. Okay. Right. We cannot write a vacuum into a wave function, right? And you can also have, say, one electron, one positron. Okay. Right. You can have many examples. Okay. It's up to you. Okay. You can also have a superposition. You can have, say, vacuum plus. Okay. You can say that this is a superposition of two possibilities. Right. Okay, so it's up to you. So you can invent a lot of things. Okay, that can be, can be used to describe a different kind of possibilities. Okay, the possibilities is a state. It's not the wave function. Okay, wave function is just one kind of possibility. Okay, it's just say that we have an electron with this kind of probability distribution. Okay, so that's the one special possibility. Okay, but in general you can have all kinds of. Okay, you can have a vacuum, you can have electron positron, you can have a superposition of vacuum and electron positron. You can have photons. Okay, right. Okay, so if we have use the direct rotation, so this will be that's a lot simpler, right? Okay, and also we know that this position operator is given by, and the momentum operator is given by. Okay, so you put this one into that one. So you can see immediately this will give us right. A lot of users write this down. Okay. Okay. So you can also look at the matrix element. Okay. So that equals to say M X M, right? So this one obviously will be 0. Okay, if M and M are not neighboring. Okay, so if M is M minus 1, right? So this is going to be this one, or this will be M over 2. Take the square root. Otherwise, it's 0, right? Similarly, you can check this. Okay, so that will be minus I plus I, always 0. Okay. Right. Okay. And then we can write down this in a matrix. So you take this one as the matrix elements. Okay. We take the matrix elements, and they find that this X can be written as a matrix. All the diagonal terms will be 0. Okay, and this will be square root of 1. This will be square root of 1. This will be square root of 2. This will be square root of 2. Square root of 3. Square root of 3. Okay, and all the others will be 0, right? So this is the X, and this P can be written as all the diagonals will be 0. And this is minus I square root of 1. This is I square root of 1. And this is minus I square root of 2. This is plus I square root of 2. This is minus I square root of 3. This is plus I square root of 3. Okay, continue this way. And all the others will be 0. Okay. Right. Okay. Of course, you can similarly, you can also find this A matrix. So that will be, 0, 0, 0, 0. Okay, and this is square root of 1, square root of 2, square root of 3. Okay, and so on and so forth. And all the others will be 0. Okay, and A deck is going to be 0. All the diagonals will be 0. Okay, and this will be square root of 1, square root of 2, square root of 3. Okay, so on and so forth. And others will be 0. Right. Okay. Right. So this is called a matrix representation. Okay, of those operators. Okay. Sometimes we put a bracket right here to emphasize this is a matrix. When there is no confusion exists, you can just use the original operation symbol to denote the matrix. Okay, the same. Okay. Right. And this matrix, you can check that the interesting, you can find that this matrix is so-called emission. Okay. This is called a emission matrix. Okay. Similarly, you can have also this one, the DAC equals to this one. So, okay, right. So they are all emission matrices, and this DAC means transpose, then complex conjugate. Okay. So this basically means that the XMM equals to XMM, the complex conjugate. So this one is the transpose. And this one is the complex conjugate. Right. So if you look at the transpose matrix, right, you just exchange the index, right? So you make the column to be the row, and the row to be the column, right? Okay. But of course, you find that this A actually, this A matrix, the complex, the emission conjugate does not equal to A. Okay. Instead, you have A. This equals to A DAC. Okay. So now you see that the meaning of this DAC, right? This just means that the emission conjugate. Okay. Okay. So this put together for the emission conjugate. Right. But anyway, so this is just a quick introduction of this Dirac rotation and this matrix representation. Okay. We're going to get more and more examples later, so you will get more familiar with this language. Okay. Don't worry too much about this at this point if you're not familiar with it. Okay. Okay. But later on we're going to use this one more and more, so you get more and more familiar with it. Okay. Okay. Let's come back to this Hamiltonian of the harmonic oscillator, right? So it can be written as omega A DAC A plus 1/2, right? Okay, so let me use one symbol notation of this one as okay. So this M just equals to A DAC A. Okay. Right. So the state will be the eigenstates. It's just 0, 1, 2, right? And the energy is just h bar omega over 2, and h bar omega plus h bar omega over 2, 2 h bar omega plus h bar omega over 2. Okay, so on and so forth, right? I know you can have a nice way to interpret this one. So from this one to this one, you plus 1. From this one plus this one, you plus 1. From this one to this one, you plus 1. And with the same energy, right? Okay, the energy changes. So this is plus h bar omega. Okay, sorry, h bar omega, h bar omega. Okay, and this one is plus 1. This one is plus 1. Okay, plus 1. So you can see that this one is it's just like adding a particle of energy h bar omega, right? Okay. So if we do this interpretation, we have this boson interpretation, okay? Right, we take this 0 as the vacuum. There's no particle, right? Okay, and m bosons. Okay, and h bar omega over 2, the vacuum 0-point energy due to vacuum fluctuation. Right. You can continue this one. So A times root of m, right? So this one is annihilation of a boson. A deck m equals to its creation of a boson. Right. And this m equals to A deck A. What's the meaning of this? So you look at this one. So the n operator is that contains of two operators. The first one is remove a boson, and then the second step is to add in a boson. So that means you take away a boson and then put it back. So what are you doing? So it's counting, right? Counting the number of bosons. Okay. So now you can easily say that. So this is the energy of a boson. This is the number of bosons, and this one is the vacuum energy. Right. So everything makes so much sense. Okay. And you can actually make a more interesting analog. Right, say if you have H equals to, say, 1/2 electric field squared plus 1/2 and B field. Okay? And this one can be written as omega, say, AK deck AK plus 1/2 summation of K corresponding to different wave vectors. Let me, this probably is too quick. Let me say, this is the energy of the electric field, right? The electromagnetic field. You can do the summation of K, and then you have 1/2 EK squared plus BK squared. Okay, and we write this E equals to summation of K cosine K x. Okay, right, times EK. So you can do this one, then you can decompose of them, right? So this way you can actually obtain that H equals to 1/2 summation of H bar omega K, and then you have the number of photons of momentum K plus 1/2. Okay, so this is just the number of photons. Okay, so we have quantization of EM field. Okay, so that's just a very quick note. Okay, of how can we use this picture to do the quantization of EM field. Okay, introduce ideas of photons. Looks like there's questions. Okay, the vacuum energy. Let me check the energy of this vacuum energy. This vacuum energy. Oh yes, sorry, that's a factor of 2. You're right. Okay. Thank you. There's another question about what's the use of these matrices. Okay. at this point, the probably just look like it's something like another representation. Okay, but later on we can see that using the matrix, actually we have another mathematical tool to solve the problems of eigenstates and eigenvalues. Okay, and later we're going to see that just by diagonalizing the matrix. Okay, so we can find the eigenstates, and also if we don't have real space wave functions, you don't have those partial differential equations, right? And the equations you're going to have actually are not partial differential equations. You're going to have a matrix equations. Okay, so later at the end of this course, we're going to learn spins. Okay, in dealing with spins, we have to use matrix instead of the partial differential equations. Okay, so there's no partial differential equations for the Schrödinger equation of spins. Okay. All right. So this is pretty much what we have learned about this kind of harmonic oscillators. Okay. So we can continue this one to 2D and 3D. Okay, and high dimensional. Okay. Okay, and a useful model for example, in many cases of one particular interesting thing is this ion traps. Okay, so that in ion traps you can have something like this one, and they can put ions right here. Okay. And then you have you apply this field, okay, such that so there's a field along this direction, okay. So this one produces the trap, two-dimensional trap along the xy, okay. But you also have a trap in this direction, right? Okay, so you basically have a v x y z, okay. That's can be written as omega x squared plus omega y squared and plus omega z squared, okay, and there's a mass term. Okay, so you can see that this omega x or y or z are just the frequency of confinement along the x or y or z direction. Okay, right. So this way you can generalize the Hamiltonian, say like a 2D. So you have this Hamiltonian just equals to px squared plus py squared over 2m and plus 1 over 2m omega x squared plus omega y squared and then y squared, right? So the Schrödinger equation will be just minus h bar squared over 2m partial squared partial x squared plus partial squared partial y squared, okay? And then plus 1 over 2m omega x squared plus 1 over 2m omega y squared and percent x y equals to e percent x y. Okay, this one is obviously you know how to solve this problem, right? So you just separate this one into, say, I write this Hamiltonian equals to hx plus hy. Okay, and each of this one have their own solution. It's just a harmonic oscillator in the x direction, harmonic oscillator in the y direction. So you have hx per psi m x equals to em x per psi m x, right? You can also have y per psi m y equals to em per psi m y, right? And of course, you can say that if you have per psi x y equals to percent mx times percent my, and immediately you have hx plus hy acting on this percent xy just equals to em plus em and percent xy, right? So this can be easily solved. Okay. So this one, of course, is called the separation of variables, right? Okay. So you just separate them, and then you can solve this one easily. Okay. And so the states can be rapidly written as, okay. So you can say that so m, x, and y, you can use these two labels to denote the states. So say mx, my, and xy. And this can be written as the product of percent mx, remember this x over LCX, and percent my, y divided by LCY, okay. So these are typical length scales in the x and y direction because they have different frequencies, right? So you can see that this LCX is just defined as h bar m omega x, right? So this is the confinement length at along x, okay. And if you choose it to be y, you just change it to be y and change it to be y, right? So that's very simple. Okay, right? And this one, all of this one percent m x over mcx, for example, are just equals to 1 over square root of 2 to the mn factorial square root of pi. I actually don't need to remember all these coefficients, okay? And m x over LCX and e to minus x squared over 2 LCX squared, right? So that's the, and similarly, you can have the same thing for the y direction, okay? Right. So the good thing that the important thing that now we have mx and y, two indices to label the state, okay? Right. I also can got the energy. That of course is mx plus 1 over 2 and h bar omega x, and plus my plus 1 over 2 h bar omega x omega y, right? Okay. Right. So this energy, you can say that you can plot this energy. So this is nx. This is nx. So this is equals to 0, 1, 2, 3, 4. 1, 2, 3, 4. So you have energy right here. This is a state. This is a state. And this is a state. This is a state. Right. So each of this one gives you a state, and the energy is just a summation of this is right. So this is the states labeled by mx and y. Okay. Right. And now we consider a special case integral that's isotropic 2D harmonic oscillator. So in this case, omega x equals to omega y. Let's call this one omega. Okay. And of course, the length scale will be the same, right? Okay. That equals to right. Right, so this is the special case now we are interested. So the potential now can be written as 1/2 m omega squared x squared plus y squared. Okay. Now the Hamiltonian can be written as 1/2 m px squared plus py squared, and plus 1/2 m omega squared x squared plus y squared. Okay. So this is so obviously it's isotropic, right? So that means it's a rotational invariant. Okay, if you do a rotation of the system, and this potential obviously is not changed. Okay. Okay. So in this case, we actually have now the E m x n y can be written as mx plus my and h bar omega and plus h bar omega, right? So now you can see that the energy is the same if mx plus my is the same. But mx and y, of course, are different for different mx and y, right? So that means you have more than one states corresponding to the same energy. Okay, so in general you can have m plus 1 states with the energy m h bar omega plus h bar omega, right? So you can see that as long as mx plus ny is a constant, the states will be degenerate. So that means this state has the same energy, and these two states have the same energy, and these three states have the same energy, and these four states have the same energy, and these five states have the same energy, and these six states have the same energy. Okay, so on and so forth. Okay, so this is say E1, E2, the E0, sorry, E1, E2, E3, E4, E5, right, so on and so forth. Okay. Right, so this one I call the okay. So they are degeneracy, okay? Of course, you can also use so you have rotational symmetry. Right. So that means if you do the rotation of the system, the state angle is not changed. Okay. So in this case, so we can use the polar coordinates so that we can separate the angles and the radial. Okay. So you have rho phi. Okay. And do this transformation. Okay. So how to transfer this one is left as access for you, and also will be talk a little bit about in the access classes next week. Okay. And so you have Hamiltonian. Now in this one, you can have the Laplacian in 2D. Okay. And then plus 1/2 m omega squared r squared. So you can see that this one only depends on the the radial. Okay. So this Laplacian 2D, if you write this one in so I will not derive right here. Okay. I just write down this one as 1/r partial r and r partial r and plus 1 over r squared, partial phi squared, okay, and plus 1 over m omega squared r squared, okay. Without running into the details, so a lot of eigenstates, okay. I can write down the eigenstates using 2 labels, okay. So, rho. Maybe let me just change that to be r, okay. It doesn't matter, okay. Okay, and again we have separation variables. And obviously you can see that the only thing that you have on phi is a differential, right? So that's why we can do this separation variables. Okay, so we write this percent ml r phi into the radial part, and then times the angular part. Okay, and with the equations for this angular part is just say partial phi okay. And then the angular part, the radial part will be okay. We actually put a I right here usually, okay, so that you have this one to be minus sign. Okay. So now you have 2 separate equations. One is for this angular part, another one is for this one. But this one, if you want, you can change this one slightly and make this one to be h bar L, right? So then you can say this one is nothing, but just the z component of this angular momentum, right? So basically, you can write down the Hamiltonian into this radial part. Okay, so this is the radial part, but you also have another term. Okay, so this is a feature that we're going to use in solving those later on central force problems. Okay, but at this point, I will leave this one because the 2D harmonic oscillator problems actually are pretty simple. Okay, so I leave this one as exercise to solve this kind of equations. Okay, just as a practice. Okay, but one thing I want you to notice is that this Hamiltonian and this LZ actually commute. Okay. Okay, so H and L commute. Okay. So this is an important feature of this rotational thing. Okay. So it's actually because of the rotational symmetry and this commute. Okay. So these two are related to each other. Okay. So we're gonna have more to say about these things, but at this point, I just want you to notice of this 2D harmonic oscillator. Okay. So later on, we have more discussion about those 3D. Okay. And you can read the lecture notes about these 2D harmonic oscillators and do some exercises. Okay. There will be homework problems on this one, but we will solve a more difficult problem like 3D, so that you can actually go back to the simple, the easy things about this 2D. Okay. So let's take a break at this point and see if you have questions. Slightly more difficult, but actually, if we write this in the Cartesian coordinates, it's still pretty straightforward. Okay? And again, we can write down this Hamiltonian into 3 parts, right? Okay. And so with this hx just equals to px squared over 2m plus m omega x squared and x squared over 2, right? And similar for y and z. Okay, so you just replace x and y and z, x to y or x to z. You got the same thing, right? And also, of course, you have this 3 components. They commute to each other. That's the one thing that you probably want to notice. Okay. Okay. So that means hx, hy, and hz commute with each other. Okay. Right. So this is the facts. Okay. And so we can solve this problem by the separation of variables. Okay, so obviously you can see that this Hamiltonian has a structure. It contains 3 parts, 1 on x, 1 on y, and 1 on z. So that means we can write down this eigenstate or the wave function into 3 parts. Say nx and x times my and y plus mz and z, right? So these are the 3 parts. And then obviously if I choose hx plus mxx equals to, you know, e mx times plus mx, and the same for y and z, right? So you can immediately obtain the Hamiltonian acting on the state okay. So you can act on this one. So this one acting on x, and this one acting on y, this one acting on z. So they do this one separately. So you got 3 separate terms, right? So this way equals to, for example, plus x and hx acting plus mxx. Because the other 2 functions do not contain x, right? So that means the Hamiltonian hx only acting on the first wave function, okay? And of course you plus the other 2 terms, right? By changing x to y. So this one, now using using this, right? So you just replace this with EMX times this one, and the same thing for another thing, right? So that will equals to very easy. This is EMX plus MX. Okay. Right. So you also have the chance that you just change this one, and then this one is just the same, the eigenfunction, the same as this one, right? Okay. So you can see that this is just the original function. Okay. So you can combine all of this together. Okay. Right. And so we have basically solved the problem by the separation variables. Okay. So let me summarize this one. So we can denote the state mx, my, and nc, just defined as percent mx, x, percent my, and y, percent mc, and c. And these are the all the eigenstates of 1D harmonic oscillators, right? So we have know how to obtain those eigenfunctions. And then you have the Hamiltonian, the 3D acting on this mx, ny, and nc. That equals to, of course, mx h bar omega x plus 1/2 h bar omega x and plus ny h bar omega y plus 1/2 h bar omega y, right? Plus mc h bar omega c plus 1/2 h bar omega c. Okay, you have this 3 terms times mx, ny, and c. So that's a solution, right? Okay, very easy to write down the solution. Okay, and also now we see that we need 3 labels. Mx, ny, mc. Okay, to denote a state. Okay, so this is a typical phenomenon in the 3-dimensional cases. Okay, so you can see that this problem is simple because it's just composed of 3 independent 1-dimensional problems, right? So each one has 1 quantum number. Okay, so we call this labels as quantum numbers. Okay. Right. Okay. So the states, you can see that you can use the 3D lattice. Okay. If you want, you can use a 3-dimensional lattice. Okay. So this is mx, this is ny, this is nc. Okay. So you can see that all of these lattice points, you have a state. Right. Okay. All right. And of course, if we have isotropic case, okay, so you have omega x equals to omega y equals to omega z. Okay, and then you find that M defined as the summation of the three quantum numbers, okay, leaves the energy EM equals to M times h bar omega plus 3 h bar omega over 2, okay. Right. So that is, so basically you can have degeneracy. Okay, there are more than one states for each EM. Okay, we call this one the number of states of the same EM. We call this one degeneracy. Okay, so then that means the states are different. Okay, but the energy are the same. Okay, so this energy just actually is very important. Okay, in physics, it's related to the symmetry and also related to the symmetry breaking. So we talk about this one a little bit more. Okay, on this. Let's see. We have this. Okay, let's check the. Take some examples. Okay. For example, if m equal to 0, mx, ny, and nc has to be 0, 0, 0, right? So that means there's only one state, 0, 0, 0. Okay. The degeneracy equals to 1. Okay. How about m equals to 1? And then you can have 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so there's 3 states. So that means the degeneracy equal to 3. How about the n equals to 2? Okay, you have 2, 0, 0. Okay, 1, 1, 0, 1, 0, 1. Okay, and 0, 1, 1, 0, 0, 2, and 0, 2, 0. Any more? And so this is slightly more difficult to count, right? 2, 0, 0, 1, 1, 0. Anything else? If it's a 2, there will be 3. If it's 1, there will also be 3. There should be 6, right? Okay, so the degeneracy D equal to 6. Okay, so you can have a 2 on anyone, or you can have 1, 1 on 2 of them, right? So you choose one state to be 2, or you choose 2 states to be 1. Okay, all right. So I like this one as an exercise for you to count. Okay, so what are the number of states that have the same energy? This 3D isotropic or harmonic oscillator. Okay, or what's the degeneracy? All right. So this is the solution of this 3D harmonic oscillator. Okay. Right. And now I want to say that if I have isotropic 3D harmonic oscillator, right? So you have V, X, Y, Z actually can be written as just a function of R, okay? Right? That equals to 1 over m omega square R square. Right? So this one make us, to be stimulated. So we are motivated to use this so-called spherical coordinates. Okay, so this R is just the square root of x squared plus y squared plus z squared, the distance. So this is the radius, right? So theta, okay. So with theta is we say that the is the azimuth angle. And the phi is the polar angle. Okay, so you can draw this in a figure. Okay, so this is the center. Okay, so this is the equator. Okay, and this is the z-axis. Suppose we have a point right here. Okay, so this distance is called r, and this angle is called theta. And suppose this is the x-axis, and this is the y-axis. Okay, and this angle is called phi. Okay, right. So this is r. The distance is r, and the angle away from the z-axis is theta, and the angle away from the xz prime. Okay, this is the angle from the z-axis. This angle is from the xz prime. Okay. All right. And also you can transfer this one back into the coordinate, the Cartesian coordinates. So this is r sin theta is the, of course, you know, the distance in the xy plane, right? And then times cosine phi. This is the polar angle, and y actually equals to r times sin theta sin phi, and z is just simply I cosine theta. Okay. All right. So this is the transformation of coordinates between the spherical coordinates and the Cartesian coordinates. Okay. Right. So with this, we can write down the Hamiltonian. So that equals to 1/2 m and h bar squared, that's minus sign. And then the Laplacian, right? And plus 1/2 m omega squared r squared. Okay. So this is a 3-dimensional Laplacian. Okay. What is the 3-dimensional Laplacian? Okay. So in the spherical coordinates, in the Cartesian coordinates, it's very simple, right? Okay. And we can also write down this one in the spherical coordinates. So it's actually 1/r squared. I will not prove this one, so you should refer to a mathematical book. And let me make sure I'm correct in this kind of change of. Yes. So this is the radial part, and then you have this is about the azimuth angle. You have one more term. That's the polar part. Okay. Right. So this is the Hamiltonian and the Laplacian in the spherical coordinates. Okay. Right. So this Hamiltonian has obviously have rotational symmetry. Right. So if you see that, you can see this one easily in classical mechanics. Okay, so this energy, you can say that the Hamiltonian just equals to P dot P over 2m plus V R, right? So this one has rotational symmetry. The reason is that if we do a rotation, of course, this one does not depend on angles, right? So that means no matter how you rotate the system, the potential is not changed. And this part is a vector dot a vector. Okay, so you know that if you have a vector, you have two vectors. Okay, if you have two vectors, say v1 and v2. Okay, and this is the inner product. So v1 dot v2. Okay, if we do a rotation, you rotate this one to, say, for example, this direction. This is v2 prime. Okay, you do a rotation on this one and do the same rotation of this. This is v1 prime, and this is still theta, right? So this will equals to v1 prime dot v2 prime. Okay, so the inner product is invariant on the rotation. Okay, so that's an important thing. Okay, so vector dot vector is invariant on the rotation. Okay, so in classical mechanics, this is obviously true that this Hamiltonian is invariant on the rotation. Okay, so that we have rotation symmetry. Okay, and we know that in the classical mechanics, we know that if there is rotation symmetry, that leads to so-called constants of motion. Okay, in other words, say that we have conserved quantities. Okay, so actually you can say that in this case is the angular momentum. Angular momenta Lx, Ly, and Lz conserved. So what does this mean? That means so if you have symmetry and this Hamiltonian and this Lx or Y or Z, okay, the Poisson bracket equal to 0. So this one means the Poisson bracket. Okay, right. But in classical mechanics, the Poisson brackets determine the motion. Okay, so if it's 0, so that means all of these quantities are just 0, right? The time derivative is just 0. Okay. So that means these are the constant motions. So you can see that you can have orbits with energy Lx, Ly, Lz as constants. Okay, and this actually is an important thing called the Reuter theorem. You have a symmetry, okay, and this one means that you have conservation loss. Okay, and the mathematical reason is because of the Hamiltonian and this Lx or Ly. Let me say all the components equal to 0. Okay. So the Roy's theorem states that if you have a symmetry, and then you're going to have this Poisson brackets between the Hamiltonian and the physical quantities, certain kind of physical quantities commute in the sense of Poisson bracket, and then that will lead us to the conservation laws. So this is what we have in classical mechanics. Okay, in classical mechanics, a state is a motion is an orbit. Okay, so this is something. Okay, in the classical mechanics, so you have orbits, and then in the orbits you can have fixed energy, of course, but you can also have a number of quantities related to the symmetry. In this case, we consider the rotation symmetry, right? And you can even consider a simpler example. You can consider, for example, the Hamiltonian just equals to p squared over 2m. Okay, that's independent of x, y, z, right? So in this case, we have symmetry is a translation symmetry. Right? And because of this one, we have the Hamiltonian and the momentum px, y, z, they have 0 Poisson bracket. So that we have momentum conserved. Right, so this is, three things about the system. So you have a symmetry, and then you have a vanishing Poisson bracket, and then you have the momentum conservation. Okay, right. So that's for the momentum. Okay, so you can do this one for the angular momentum for momentum. Okay, sometimes you have some other quantities. Okay, but anyway, so that's what we have in classical mechanics. So what about quantum mechanics? Okay, so what about quantum mechanics? So let's look at this Hamiltonian, for example. The quantum mechanics Lord theorem. We also have a symmetry. Suppose we have a symmetry. Okay, and then from this one, we're going to have actually, instead of a Poisson bracket, we have a certain quantity, say A, equal to 0. So this one actually is related to the Poisson bracket in classical mechanics, according to Dirac. So Dirac established that if you have a Poisson bracket between the Hamiltonian and the physical quantity, or any two physical quantities, and then corresponding in quantum mechanics, you should have the commutator between these two. Okay, so that's what Dirac has derived. And then from this one, we know that this A is a constant. Okay, that means conservation. And I was why? Okay, please stay tuned. Okay, I will explain this one a little bit later. Okay, so why if A commutes with H, you're gonna have this one to be a constant. Okay, but before that, let's look at the Hamiltonian of the isotropic 3D harmonic oscillator. So the Hamiltonian, remember, can be written into this form. So one is this is 1 over r squared partial r and r squared partial r, right? This is the radial part, okay? And of course you have the potential. So these are the purely audio part, radial part, but you also have another term that is 2m r squared. And what's inside is actually is minus h bar squared. 1 over sine theta partial theta and sine theta partial theta. Okay. And then plus 1 over sine square theta partial phi squared. Okay. So this one is a very interesting term actually. So this one, it turns out it is just the momentum, angular momentum squared. So this one actually equals h bar over I squared. And then it's 1 over sine theta partial theta sine theta partial theta plus 1 over sine square theta partial phi squared. Okay, right. So that means, so if you have this one, we got the Hamiltonian will be simply minus h bar squared over 2m 1 over r squared partial r squared partial r, okay, and then plus 1 over m omega squared r squared. Okay, this is the radial part, and then plus 1 over 2m is only r squared. Okay, right here, and what's left is just l squared. So look at this Hamiltonian. Okay. So check this Hamiltonian. So immediately you can see that, of course, we have a symmetry. So one important thing is that first we have rotational symmetry. Okay. And secondly, you can see that now we have a Hamiltonian commute with Lx and with Ly with Lz, and also, of course, with L squared. Okay, right. So let me check one of this, okay, and then you're going to see why. Okay, let's check one. Okay, and this is the simplest one. The reason is that Lz is just simply h bar of I partial phi, right? Now you can check that the Hamiltonian has some kind of things that contains only on the R. Okay, so we say that this part is just this part. Okay, and then you plus one more term, that is 1 over 2m r squared L squared, right? Of course, you know that if you have anything on the R and partial phi should equals to partial phi and anything just on the R, right? So that means these two commute. And also we know that Lz and the total angular momentum squared is also 0, right? Okay, we have these two. Okay, so from this one, so immediately you got a H and Lz should be commuting. Okay, so the commutator should be 0. Okay, That's very simple, right? And then you ask how about the Ly and Lx? Lx and Ly actually are very kind of clumsy if you really want to do it. But let me tell you how to do it, okay? A better way is that if you write this, you can actually write Lx equals to y times Pz minus Cpy. That's easy, okay? And then you can check H and Lx equal to 0. And also, similarly, for y, okay? It's easier to do in the Cartesian coordinates, but actually, you don't need to do the calculation. Okay, you can just say just by argument, you must have this one equal to 0, and also for y. The reason is very simple, right? Because it's just choice of coordinates, right? So you can define the spherical coordinates not another z direction, but another x direction. Okay, and they got the same form of the Hamiltonian. But now the Lx will have very simple, form. Okay, just the same as the Lz. Okay, so it's just up to you to choose which axis to define this spherical coordinates, right? So that's because z, x, y is up to your choice. Right. So if you have the Hamiltonian compute with Lz, so it also should compute with Lx and Ly. If the Hamiltonian, does not specifically, explicitly depends on x and y and z. Okay. Okay. So that's the simple argument. Right. And of course, and then, you know that this one will commute with L squared, right? Okay. So that's a particularly interesting thing that we're going to have, okay? Right. So let me come back to this point. So now you have this one, and then actually, and then from this, we should also have H, L, Z, and L squared can have simultaneous eigenstates. Okay. I will talk more about this one in general theory, but let's just write down the solutions for the 3D isotropic Hamiltonian. Okay. Right. So isotropic 3D Hamiltonian in r theta phi. We have seen that this one is minus h bar squared over 2m, 1 over r squared partial r and r squared partial r plus 1 over 2m omega squared r squared, right? And plus 1 over 2m r squared and L squared. Okay. And L squared depends only on, it's only an action on theta and phi. Okay. So that means we can write down this wave function, the eigenstates, as a radial part and a theta phi function. Okay. So you can say that this is L squared y theta phi, say equals to a certain kind of number. Let me write this as L times L plus 1. but L could be any number. So that means this one could be any number, right? So it doesn't matter. But just for convenience, in the later, derivations, I just write this one. So this is just a choice of, it's just a number. It's just a real number, okay? And dimensionless, because I write this, because L has the dimension of h bar, so L squared has the dimension of h bar squared. Theta phi, right? But remember, this L squared is also something like a minus 1 over sin theta, partial theta, sin theta, partial theta, minus 1 over sin squared theta, partial phi squared. So you can see that again here only contains partial, does not depend on phi. So this is independent of phi. Okay, so that means I can furthermore write this function of theta phi as separated into, say, for example, p theta. Let's say theta and the phi as a function of phi. Okay, so it turns out that the solution. Now you can have partial phi. I put a IH bar right here. On this one, that equals to LZ and the phi. Say I can write this as another number m times h bar. This m is again is a dimensionless real number, right? Okay. So that means essentially eventually you will get the Hamiltonian acting on this R, and then this function of theta and this function of phi, okay, equals to the energy and R and the theta and the phi. And this simultaneously, you can even go back, right? LZ on this function. Right, because this one is just a function of R and theta, so LZ does not act on this one, only act on this. So that equals to m h bar, okay, phi. Okay, since this has m, let me just denote this. Put the m right here. Put m right here. Put m right here. Put m right here. Okay. Right. And then for the, we're going to have L squared. Okay. This R theta and the phi m phi just equals to L times L plus 1, okay, and h bar squared, okay, R theta and the phi, okay, and this has a m, right? But since this has an L right here, so let me call this one L, but it could depend on m, right? Because you need to put back this eigenstates of this partial phi over there, okay? So that means this is a function of L and M, okay? And this is a function of M and M. So this is L and M. This is L and M, okay? And of course, if you look at the energy, this energy, now once you got the eigenvalue of this one, this has a constant, so that's determined. So this one just depends on its M and L. So this is M and L. This is M and L. Right. So that is the general solution of this one. So the specific form will be discussed later in general, context of central force problem. Okay. But if we summarize that here, this is like quite a clumsy. Let me just call this state M, L, M. And this should have is eigenstate of LZ. That equals to M H bar, M L M. You should also have this M square, L square on this one, M L M. That equals to L times L plus 1, H bar square, M L M. And the Hamiltonian on this one, that equals to energy M L M L M. Okay. So you have 3 quantum numbers. M L M. Okay. And this one is called a principal. This one is called the angular. And this one is called the magnetic. There's a reason for this names, okay? But so far, it's just so-called, okay? Right, so we're going to find the more specific forms of these solutions. But that gives us the general structure of the solution in terms of spherical coordinates. Okay, it looks like a more complicated than the solutions in the coordinates. In the Cartesian coordinates. The reason is because for the harmonic oscillator, this R square can be easily written as X square plus Y square plus Z square, right? But on the other hand, so this one actually, so this one, just similarly, are more complicated than MX, NY, and NC, right? Okay. But the point is that it captures the symmetry, the essence of symmetry. Okay. And so more general for central force problems. Okay. Right, so you can consider the central force problem, for example, here you have R square equals to X square plus Y square plus Z square. That's very simple, right? So you can see that, so MX, this one can be easily transferred back from MX, NY, and MC, okay? But what about if 1 over R? That's 1 over X squared plus Y squared plus Z squared, okay? So in this case, no easy separation, right? Actually, there's no separation of X, Y, Z, right? So then you cannot use the NX, NY, NZ to label the states, okay? Because in all these X, Y, Z, they are entangled together, okay? You cannot easily separate them, unlike in this case. So you have a separation. Okay, so right. So for more general central force problem, so you would like to use this spherical coordinates, which is similar to be more complicated, but it's more beautiful and capture the essential features of this symmetrical problem. Okay, so we're going to have more to say about this symmetry and about the solution of the central force problems. Okay. And I will use this 3D isotropical harmonic oscillators sometimes as an example, okay, to show the features of this, okay. All right, and later we'll also apply this one to the 1 over R potential. That is basically the hydrogen atom problem, okay. Okay. Right. So let's stop right here today and see if you have questions.